Thanks, Jenny.
Thanks.
Okay, thank you, Jenny. Let's get to the last of our GCEP speakers, and our last one is Charlie Barnhart. He's a postdoctoral scholar at GCEP. He does energy systems analysis, so he looks at the big systems, and he's going to give us an overview of some of the work that we do at GCEP on energy systems analysis.
All right, I'm truly honored to be here, and I really would like to thank the Reliance Foundation for hosting us. The village visits we did the last 2 days were life-changing, and I think it only further promoted the desire in all of us that attended to promote human welfare. And so today I'll be talking about energy systems analysis. I'm going to focus particularly on some work I've done that looks at the energetic performance of pairing renewable resources with storage technologies. So my undergraduate education is in physics, and that's tainted my thinking ever since. So I look at the world in terms of kilograms and joules, not in terms of dollars. And so as an energy systems analyst, I track material and energetic costs, not monetary costs. But with this, we can inform research decisions, capital investment, and policy decisions. And so as an outline for the talk, I'll first look at the energetic performance of resource generation technologies, then the energetic performance of storage technologies, and finally the energetic performance of a microgrid that pairs these technologies together. All right, so one metric we use as energy systems analysis is the energy return on invested. It's an ecological principle. And so we can imagine that this fox is a society, and it has to invest a certain amount of energy to acquire energy. And she necessarily needs to consume more calories from that mouse, get more energy from that mouse than she spent trying to capture that mouse. If she does this, then she'll have an EROI greater than 1, and the society's economy will grow, it will become more productive. If she fails to do so, then the society will shrink. And so what is the EROI value, or the energy return on investment value, for different renewable low-carbon technologies, particularly the ones that we've all identified as having massive potential for supplying society with energy? This analysis was done by my friend and colleague, Mick Dale. He's also a postdoc at GCEP. Unfortunately, he wasn't able to attend, but it's for a very happy reason. He's getting married. And so he's looked at the EROI value from several different life cycle assessment studies, massaged the data so that they're dimensionally consistent. And he's shown that solar wafer photovoltaic technology has an EROI value of about 8, and onshore wind turbines have an EROI value of 86. Now, these are both great EROI values. They're providing net energy to society. The reason why wind is an order of magnitude greater than solar is because solar, the production of solar photovoltaics is more energetically intensive. It takes a lot of energy to purify silicon to manufacture the cells. All right, so great. These resources have good EROI values, but the trouble with them is that they're intermittent. They're variable. They depend on weather. This plot shows, well, it's always good to talk about the axes first. So on the y-axis is power production, or power demand, and on the y-axis is time of day. And what's plotted here are 30 days of wind production in blue, 30 days of solar production in yellow, and 30 days of power demand in red. And as you can see, there's a high degree of anti-correlation between power supply and power demand. But there is some good news here too. The average values are the bold lines with the black interior, and as you can see, solar and wind complement each other. There's solar power in the day, of course, and there's higher wind power during the night. So to accommodate these intermittent and variable resources, we necessarily need to increase power grid flexibility. In the developed world, we have several options to do this. I won't go into them in the interest of time. But in a microgrid situation, the situation that exists in these rural villages, the only real option for supplying reliable power that stems from these intermittent resources is battery storage technology. And so I've analyzed the energetic performance of these storage technologies. My analysis includes 3 electrical chemical storage technologies: lithium-ion, sodium sulfur, and lead acid, 2 flow battery technologies, vanadium redox, and zinc bromine. And I've also analyzed 2 geologic storage technologies. These aren't appropriate for a small-scale village, but they're important to include in this talk because it provides a benchmark for these distributed technologies. And so the metric that we developed at GCEP is analogous to the energy return on investment. It's the energy stored on invested, and Sally mentioned this in her presentation. So it's the total amount of energy stored over the lifetime of the entire lifetime of the technology divided by the embodied energy required to mine the raw resources, assemble them, deliver them to a factory, manufacture the technology, and then deliver that technology to its place of use. It's a fairly simple equation. It's 4 variables. So the energy stored is comprised of the total number of charge-discharge cycles. That's the cycle life lambda. And then this total energy storage will be mitigated by inefficiencies. And so we multiply that term by the efficiency eta. And then some battery technologies can only be discharged to certain depths. Otherwise, irreversible chemical reactions occur, physically disrupting the battery and greatly limiting its cycle life. So this total energy storage, again, is divided by the embodied energy of the cell. And here are the results. You've seen these before. The energy stored on invested values are much greater for geologic storage technologies than they are for battery storage technologies. And we've also calculated this in terms of electrical energy, embodied electrical energy. Electrical energy is higher in quality by about a factor of 3 than primary fossil fuel energy, and so you need to invest less electrical energy. So the ESOI value for these storage technologies are in the relative same position, but they do perform a little bit better if they're manufactured with electrical energy. All right, so why is this the case? Why are geologic storage technologies performing so much better than battery storage technologies? I've performed a very crude sensitivity analysis, one such that I could understand it, and we can look at the different variables that go into the energy stored on investment equation, and we can see that efficiency varies by about a factor of 1.5. Cycle life, which is depth of discharge dependent, varies by about a factor of 30. And the embodied energy varies by about a factor of 7. So clearly, the greatest potential for increasing the energy stored on investment value for these battery technologies is increasing cycle life. All right, so we now know the energetic performance of the resource generation technologies. We know the energetic performance of the storage technologies. So what happens when we pair these together in a microgrid? What is the grid scale energy return on investment value? And how can we optimize that? I don't have time to go through a full derivation of this theoretical framework, but I'll walk through the basic schematic framework. So a solar panel here has some energy intensity, some embodied energy, epsilon R, and then it delivers 1 unit of energy to the grid. That energy can go directly to the power, or fraction of it can pass through storage. So the fraction phi that passes through storage will incur further energetic costs. Now energy needs to be expended to build the battery, and then some energy is lost due to the inefficiency of the battery. The resultant equation is this grid scale EROI, EROIG, and we can compare this to a simple curtailment equation. So say that fraction that didn't go through storage because the storage device wasn't there was simply curtailed because that energy wasn't useful at that particular time of day. Now here are the results from these 2 equations. There are 2 plots here, and this shows again, the grid scale energy return on investment value. The plot on the left is for solar PV. The plot on the right is for wind technology. The y-axis shows the grid scale EROI, and the x-axis is the fraction of energy that passes through storage. There's the two black lines bisecting the plots is the curtailment EROI. Now that's a little bit easier to understand, so I'll discuss it first. If none of the resource is curtailed, then the EROI is the original resource EROI. So if phi equals 0, then the EROI is 8 for solar, for example. And if all of it is curtailed, then the EROI is reduced to 0. So now let's discuss the tricky bit. So if a fraction of it passes through storage, then it has this behavior. Now some of you may recognize an equation that looks like this. It's called the sum of reciprocals. And so it behaves the way resistors do in a parallel circuit. And so as the fraction that goes through storage increases, the weight of the EROI value and the ESOI value become comparable, such that the grid scale EROI will be bottlenecked by the smaller of those values. So the EROI grid for solar technologies, when it passes through storage, performs quite well when compared to the EROI for curtailment. This is because solar energy is energetically expensive. So it makes sense to spend more energy on a storage technology that can preserve and capture as much of that expensive energy as possible. Whereas wind energy is energetically cheap. And so to build a storage technology will actually cost more energy to capture that wind than to simply allow that excess wind to be curtailed. Now this isn't to say that there isn't a value in storing that energy. These ERI values are still spectacular for storing wind energy. It just says maybe there's other uses for this wind energy other than storage. Building storage technology for wind might not be the wisest use of society's energy. All hope is not lost for battery technologies. So at GCEP we try to identify research directions, and we can rearrange the equation for that energy balance and then substitute the variables for ESOI and come up with the following inequality. And we can see that to achieve a cycle life value such that we can the energetic performance of storage can beat curtailment, the cycle life for storing wind technologies needs to be about 12,000 to 18,000 cycles. This is about 2 to 18 times present day values, which are illustrated by these ribbons. And this is achievable. GCEP is funding one such technology that's achieving 40,000 cycles. It's a lead acid battery type technology. It can sit, it's stationary, it sits, it's filled with water, and it's based on an open framework of Prussian blue analogs. Now, Prussian blue provides this mineralogical framework of metals and transition metals that builds this cage that the monovalent and divalent elements can enter and exit over and over and over again without mechanical stress. And so this leads to really, really high cycle life. And so this work by Professor Huggins and Professor Shui and their postdocs have demonstrated over 40,000 cycles. If we plug that 40,000 cycle value into the energy stored on investment equation, then that lead acid technology now achieves an ESOI value of 90, which allows it to store wind in an energetically favorable way when compared to simply curtailing that resource. All right, so let's bring this back to India. What are the implications and conclusions of this energetic performance of a microgrid with renewable resource and an energy storage technology? Well, wind and solar resources firmed by storage are net energy positive, so that's a great thing for society. They're also low carbon. But wind is energetically inexpensive, so we should probably think of more creative uses for that excess energy or unneeded energy than building storage with it. So this is a workshop, and I don't have all the answers, but it's important to provide questions. So hopefully in the discussion sections tomorrow, we can talk about some of these things. Could we pump aquifers with that excess wind power? Could we have a mechanical system and an electrical system? Can we drive irrigation? On the other hand, solar PV is energetically expensive, so we should store it. And I think microgrid situations, PV battery couplings, could be quite useful in providing lighting and other energy services. And we should increase the cycle life of batteries, make them more robust and durable. And I thank you very much for your time.